So welcome everyone to our first seminar for spring term 2021. We are delighted to have with us Philip Mocz, Dr. Philip Mocz. He did his undergrads on mathematics and astrophysics at Harvard University. Then he continued on a PhD at Harvard University. After that, he was awarded the prestigious NASA Einstein Fellowship, and he moved to Princeton. And since 2020, he's a Lyman Spitzer Jr. Postdoctoral Research Fellow in Princeton University. That's a illustrious CV. Philip's interests are on theoretical astrophysics and cosmology, including problems of dark matter, especially fuzzy dark matter, which seems to be a very hot topic, but not hot dark matter. And also he's interested on computational physics. So Philip has also received numerous prizes and awards that I don't want to get more of his time to mention all of them. But he has received awards on for his work on cosmology and for his academic performance. So Philip, you can share now if you want your presentation, and we are listening. Thank you very much.
Okay, thank you very much, Konstantinos, for that introduction, and very happy to be visiting the university here in Patras virtually. And let me share my screen for my talk. Yeah, so today I'd like to talk to you all about my work on fuzzy dark matter and comparing fuzzy dark matter to other common cosmological models for dark matter, including cold dark matter and warm dark matter. And in this talk, I'll give a bit of a background on this dark matter model and also talk about, in particular, simulations of first galaxies under these three different types of dark matter cosmologies. So as Konstantinos, you said, I'm a postdoctoral fellow currently at Princeton University. And so the outline for my talk today, I will first introduce FDM, followed by a discussion of these cosmological simulations that use full physics capabilities. By full physics, I mean we have the dark matter component and the baryons and star formation and feedback. And I'll highlight this idea that which the simulations show that first galaxies, which tend to be low mass and form early at higher redshift, maybe redshift around 6, these galaxies are unique probes for the physical nature of dark matter and can be strikingly different under different dark matter assumptions, even though the more massive galaxies might look more similar. And these galaxies are not yet observed because they're faint and far away, but next generation telescopes like the James Webb could see this population, and after that we'll be able to learn a lot more about dark matter. And so I'd like to also talk about the simulation methods that go into creating such cosmological simulations, and I do spend a lot of time on code development as well, and coming up with new methods and scaling these to high performance clusters. So I'd like to talk a little bit about how you solve fuzzy dark matter on a computer. And so I'll highlight the spectral solver that I've developed. And then there's the baryonic component too. So I'll say a little bit about that, how we use a moving mesh approach to solve the magnetohydrodynamic equations for the baryons. And this was work I've done for my PhD. And then I'll take a step back and talk a little bit about just idealized simulations of a single FDM halo in a closed box, and what's the final steady state virialized structure of such halos, to build some basic properties like the understanding the core to halo mass relation in such in fuzzy dark matter halos. And then I'd like to zoom in on other interesting features of fuzzy dark matter, and these include the unique small-scale substructures. And I'll highlight 3 student works here, touching upon interesting features that are different from CDM predictions. And these are related to the processes of dynamical friction, dynamical heating, and I'll also talk a little bit about how the fuzzy dark matter can concentrate around supermassive black holes, and what are some of the observational constraints there. And then finally, I'll talk about this interesting connection between the equations of fuzzy dark matter and the equations for cold dark matter, and how one equation approximates the other. And so fuzzy dark matter, as I'll get into soon, is a quantum wave description for dark matter. And so you have quantum mechanical properties that manifest themselves on the scales of galaxies. And cold dark matter is a purely classical phenomena. And the former is described by the Schrödinger boson equations, the latter by the Vlasov boson equations. And I'll talk about how these 2 equations actually approximate each other, particularly in the limit that you make the fuzzy dark matter particle mass large. And then I'll just conclude with some areas of future direction needed to be able to better constrain the fuzzy dark matter model and add in more physics. So this is also, before I begin, just some work that I do in collaboration with a lot of people. I'm highlighting some of my close collaborators here who are young faculty members across the United States mostly, but also in Cambridge, United Kingdom. So it's really a work with a fantastic team. So let's begin. What is fuzzy dark matter? And I'd like to just remind everybody about the nearly century-old problem that astronomers and physicists face, which is that for almost 100 years, we've been wondering about what is the nature of this mysterious matter content in the universe that makes up 84%, and it's thought to govern and hold cosmic structures together through its gravity, but we don't know the nature of this dark matter that fills the universe. Whether it's a particle, and if it's a particle, what is its mass, and how does it fit into the standard model? How does it interact with other particles, if at all, other beyond gravity? So there's certainly a lot of observational evidence for dark matter. The early work comes from observations of rotation curves in the Milky Way, which I'm sure this audience is familiar with. And this is work by Vera Rubin. And there's also evidence for dark matter in the large-scale structure and clustering of galaxies. You're able to constrain dark matter properties from the cosmic microwave background. You see evidence for dark matter from lensing. And finally, even galaxies, low-mass galaxies that appear to show no dark matter in them, such as these recent ultralight faint, ultra diffuse faint dwarf galaxies by Van Dokkum et al. Even these galaxies place constraints on our theories for dark matter, and we have to be able to explain, why we have multiple populations of low mass galaxies and how we can get some without any dark matter contained in it. And so, so here are listed 3 possible candidates for what dark matter could be. The standard cold dark matter paradigm, such as the WIMP, the weakly interacting massive particle, is around a GeV scale, something that people have been trying to find through particle collider and detector experiments. There's no evidence so far, and that parameter space is slowly being ruled out. we have, but it still remains the leading theory in the field at the moment. So on this mass scale, we have the electron here. At lower masses, you have the warm dark matter model, where the particle mass might be on order of a keV scale to be able to be consistent with observation. So what happens in warm dark matter is you have a lower particle mass, and this dark matter fluid that fills the universe has some velocity dispersion in the early universe, has some temperature that suppresses small scale structure formation, and you need about a keV mass or larger to make sure that you don't erase too much substructure. And finally, there is this fuzzy dark matter model, which is you assume that your dark matter is an ultralight boson, and this fills the universe. And in this case, small scale structure can be suppressed by the quantum uncertainty principle. If you calculate the de Broglie wavelength for such a small particle, it can start affecting cosmic structure. And you want to make sure that the particle mass is not too light so that you don't erase everything in cosmology. So usually when people talk about fuzzy dark matter, there's this fiducial value of 10 to the minus 22 and above. And that's interesting. So just to summarize, the fuzzy dark matter model, you assume that dark matter is a cold ultralight scalar field, a boson particle, and such a particle, such a field does have zero temperature in the early universe and ends up forming, since it's a Bose-Einstein condensate, where all the particles share the same wave function, and the dark matter has microscopic quantum properties. And so you have this self-gravitating superfluid which experiences this quantum pressure, which can hold back gravity from collapse. And I've mentioned some fiducial values before. So the particle mass might be ultralight 10 to the minus 22 eV. So if you assume a halo with a velocity dispersion of 100 kilometers per second, this will roughly, and this particle mass, then you'll be able to calculate that the de Broglie wavelength is roughly a kiloparsec. And this system is governed by the Schrodinger boson equation, as I've written it here. So psi is the wave function, and here psi squared is normalized to give you the macroscopic dark matter density. And you can see that this is just Schrodinger equation, where the potential field is just the self potential that's obtained from gravity by solving Poisson's equation in the middle. And so some of you, this might seem like a very unusual model for and very different model for dark matter than which you might be familiar with cold dark matter. So I'd like to motivate it and list the historical motivations for such a model. And there's both motivations from the astrophysical side and the theoretical physics side. So from astrophysics, currently cold dark matter is the leading paradigm, which just assumes no particle physics and something that's collisionless. But such a model faces some small scale challenges, and this includes usually these challenges have to do with the number density and the statistics and as well as the size and the shape of the low mass galaxies, that the satellite galaxies of Milky Way like galaxies. And this includes the deficit of dwarf galaxies, or the missing satellites problem, where there are, in a cold dark matter simulation, you tend to find more dwarf galaxies than observed. Although this gap has slowly been closing with time, as observations have found more satellites around the Milky Way. But there's still a problem related to the specific abundance of and the size and shape of the satellite galaxies. This is usually classified as the too big to fail problem, and there's a related problem with the abundance of isolated dwarfs. And I mentioned, so in addition to the statistical properties, there's also of the population, there's also potential problems with individual shapes of dark matter halos as inferred from observations versus what's simulated in a cold dark matter simulation. And this is usually the core cusp problem, where n-body simulations of cold dark matter predict cuspy center, whereas observations of many dwarfs, many dwarf galaxies predict cores. And there's a question of whether there is a question of whether baryonic feedback is responsible for that. But another solution might be that it's the nature of the dark matter that sets the core size and the shape. So there's also motivation from theoretical physics, where a candidate particle for fuzzy dark matter is the axion, and axions have been predicted to solve the strong CP problem in theoretical physics. Typically, and this goes back to Pechi-Quinn theory from many decades ago. And typically, such particles are ultralight. So there is this the original motivated mass for such an axion in QCD is maybe around 10 to the minus 4 eV, which could also be a good candidate for dark matter. But there are also models in theoretical physics which provide more recent ones that provide ultralight classes of axions of around 10 to the minus 22 eV, which is also which is my focus today. So to summarize some of the important observational constraints before I started my simulation work, there is constraints on the fuzzy dark matter particle mass from CMB. Basically, you want to make sure that you do not erase too much of the substructure. So if you make the boson mass smaller and smaller on the left, I'm showing the initial power spectrum. I'm showing the initial power spectrum for the fuzzy dark matter model and changing the axion mass. And if you're making it smaller and smaller, then you're cutting off more and more of the small scale substructure in the early universe from the suppression due to the quantum uncertainty principle. And at some point, this becomes inconsistent with the CMB. So work by René Flajek here on the right has excluded this mass range between 10 to the minus 24 and smaller, as having erased too much structure in the CMB. There's this interesting regime where if the particle mass is made so small that it's 10 to the minus 32, then it can start acting as dark energy instead and be responsible for the expansion and acceleration of the universe. But that's a whole other model, and I won't get into that. But the constraints from CMB is that you need the particle mass to be larger than 10 to the minus 24. There's also very nice constraints from the Lyman alpha forest, which tend to probe structures on megaparsec scales at redshifts between 3 and 5 or 3 and 6. And the idea here is that Lyman alpha forest traces the dark matter power spectrum, and this can be compared against simulations. And typically the result from this type of comparison is that the particle mass has to be greater than 10 to the minus 21 eV. Otherwise, there's not enough megaparsec scale power in the Lyman alpha forest at around redshift 5. And there's a few caveats to this statement, and including the need to actually perform self-consistent simulations that capture all the nonlinear structure formation rather than making some analytic assumptions about or using linear theory. So that's why I have this tilde sign here for this mass constraint. And finally, there's also constraints from studying the structure of dwarf spheroidals around our Milky Way. In particular, Fornax and Sculptor provide great constraints. So the idea here is that these two satellite galaxies of the Milky Way, the velocity dispersion in the stars and their radial distribution allow us to infer that these galaxies have large, low-density dark matter cores, very different from what you'd predict from cold dark matter models. But in the fuzzy dark matter model, and I'll get into this in my research, but you end up predicting a soliton core at the center of halos. And these tend to be large and low density and have a one parameter family of solutions. So it's a very rigid model that you can then fit to each of these galaxies, and the axion mass is also an unknown that can be constrained. And such work suggests an axion mass of around 10 to the minus 22 to fit both data sets. So these are so some of the recent constraints are summarized in a bunch of papers. I'll just throw it up here for a second. But there is, there is this slight tension, which I'll call the catch-22 problem, which is that you want a small boson mass to describe, large cores at the centers of halos and describe these dwarf satellites, Sculptor and Fornax. But you also want to make sure that the boson mass is not too small, otherwise you will erase all your satellites and substructure. So to resolve this problem, we need to take the fuzzy dark matter theory to the next step with some high performance realistic computations that include dark matter and baryons. And this is still ongoing work, but I'd like to share with you some of my first results from the past couple of years. Looking at these, focusing in on, rather than full, really large box cosmological simulations, focusing on smaller boxes and diverse galaxies that may form. So let's begin. So these simulations include baryon star formation and feedback, as well as the quantum mechanical wave effects of the fuzzy dark matter. The initial conditions are generated with axion cam at redshift 127. These simulations were run on Stampede 2 primarily for 5 million core hours. And the limitation of that I face currently is that the method is still very memory expensive because we need to resolve these quantum mechanical wave features in the dark matter and the phase structure. So the study is currently limited to small box sizes around a couple of megaparsec and higher redshifts to be able to resolve everything properly. And so, but this makes it an ideal study for the first galaxies that form in the universe under different dark matter models. And this turns out to be very interesting, as I'll show you. So just highlighting some of the large scale features in the box, I'm going to simulate 3 types of dark matter from redshift 127 to redshift 6, fuzzy dark matter, warm dark matter, and cold dark matter, and with the same initial seed. And I have warm dark matter in quotes because it's not quite a warm dark matter model. It's actually, I'm using the fuzzy dark matter initial power spectrum to make and I'm assuming zero velocity dispersion. So it's warm dark matter like in the sense that it's sort of a it's warm dark matter like in the sense that I am neglecting the wavelike properties of fuzzy dark matter. And you do have this initial cut in the power spectrum, but it does not include a velocity dispersion at higher redshifts. And so large scale structure, you can see right off the bat that in the warm and fuzzy dark matter models, you erase a lot of the substructure, and the warm and fuzzy dark matter, and this is primarily due to the initial conditions. And at this level, the warm and fuzzy dark matter looks very similar in the projected density of dark matter, and with a lot less substructure, which I said. But when we zoom in, we can see interesting differences. So here is a slice of filament in these simulations, and I just want to highlight some qualitative important features of the 3 models. So in cold dark matter, you don't have a physical length scale in your equations. It's everything's self-similar and you end up forming subhalos on all resolutions, on all scales down to the resolution scale. And so structure formation is entirely scale-free, self-similar. In the warm dark matter model, you do include a scale, which is the suppression of power below the initial cutoff scale. And so you stop forming subhalos below some length scale, and instead you do end up forming these nice smooth filaments with some caustic features. So caustics are locations where density might formally spike to infinite, and there's a shell crossing in your velocity, in your phase space, where there's multiple velocities at one location. And in fuzzy dark matter, some these features get replaced by interference patterns, as you have waves traveling with different velocity vectors. And the caustics, these infinities, become regularized by the quantum uncertainty principle. So looking at things in slightly more detail, again, we have to zoom in on this filament here on the big box. And these are first structures. So maybe some of these halos are 10 to the 10 solar masses or smaller. But the box also has, in addition to the dark matter, it has gas and stars. And then I'm again showing these slices of the dark matter halos. This is at redshift 5.5. And one interesting we can see in the gas and the stars is that, so the first structures, once you, in the fuzzy and warm dark matter, are quite filamentary. And so you've switched on, so these are filamentary because you've introduced this cut in your initial power spectrum, and then there's no collapse beyond a certain scale. And so the initial random Gaussian field conditions end up giving you these filaments, and with some deep potential wells, deep enough to collect gas and form stars along the filament. So this is, so these objects might be some of the most striking, the areas where you can perhaps see some of the most striking differences in the predictions of, fuzzy and warm dark matter, like models versus cold dark matter. And just to highlight this, we put the simulations through synthetic observations and made predictions for what JWST might be able to see for these earliest galaxies. So this is what the gas in the stars might look like in a typical JWST band at redshift 5. So upon first light, we might be able to learn something right away about the nature of dark matter. And so one interesting thing that we found in the simulations is we found a nonlinear structure formation channel. So the first structures, as I said, were actually filaments, and these filaments are unstable, and there can be further collapse in the filaments. So the filaments, so here is showing radial profile of a slice in the filament, and I'm comparing fuzzy dark matter and warm dark matter. And the fuzzy dark matter shows a core, and warm dark matter shows the cusp. And this core can be fit by a cylindrical soliton-like solution, but this is fundamentally unstable. So what ends up happening in the core is that you do have, at later redshift, you do have further collapse of this filament into a soliton, and you form, you form solitons with halo mass that's beyond the, it's a couple orders magnitude below what you'd predict for the minimum mass halo from linear formation theory. So, and the other thing to point out here is that the gas in the stars follow this chord-like distribution in the fuzzy dark matter model. So they trace the dark matter. When you're looking at the evolution of the dark matter power spectrum, and here I'm comparing cold dark matter, warm and fuzzy again, at various redshifts. And there is definitely this initial suppression of small scale power due to the initial conditions, which you can see still persists at later redshifts. And the fuzzy and warm dark matter power spectra are similar, but you do have this excess of small scale power in the fuzzy dark matter model due to interference patterns. I'll skip this slide on star formation history, but I'll just briefly highlight that star formation is delayed in the universe once you introduce this cut in the initial power spectrum. And even at redshift 5, given our baryonic assumptions, you can see that there's a factor of 2 fewer stars in this early universe. So this could also change depending on the precise prescription for your star formation and baryonic feedback. But so I can envision a project where you can take these types of simulations and set further constraints on the boson mass by thinking about the limits that are set by reionization in the universe. So to summarize, what the simulations have shown so far is that first galaxies are quite a unique probe for the physical nature of dark matter. So JWST will open an observational window into this emergent world and be able to distinguish between certain classes of dark matter. And in fuzzy dark matter in particular, we see that primordial stars can form along dense filaments in addition to just forming inside halos. And these filaments can show coherent interference patterns. They develop a cylindrical soliton-like spine, which become unstable and can collapse further into cores, into soliton cores, which are soliton core dominated halos, which are quite low mass, and then the gas in the stars trace the core nature of the dark matter. So we're roughly at halfway through the talk. So I'd like to give you open up the hood and show you a sneak peek into some of the simulation methods that go behind this. And turns out that the evolution of the Schrodinger boson equations, it's quite simple but quite expensive. So I use a second order spectral method, which couples nicely with the other parts of the code. So it's based on applying unitary operators, which preserves the nature of this unitary evolution of the wave functions. So, and everything is accomplished using fast Fourier transforms. So we can take the density field, apply fast Fourier transform, divide by k squared, which is the Nobla squared operator in the boson equation, in order to recover your potential. Then you can apply this potential to evolve the wave function using this unitary operator in equation 3 by applying a half time step kick. You can apply the drift operator, which propagates your waves in your superfluid. This is the kinetic operator in the Schrodinger equation. And this is again best accomplished by taking a Fourier transform. So your Nobla squared in your Schrodinger equation becomes a k squared, and then you invert Fourier transform back. And then you close off the computation with another kick. And I'd just like to highlight that with some recent work we've been in the past few months, I've been actually thinking with some quantum information scientists how these methods can be adaptable in the future to quantum computers. So the baryonic physics are of course solved very differently, and I'll just throw up the slide to say that the baryonic physics for the fluid dynamics part, I used the Arepo code developed by Volker Springle, and for which I've developed an MHD module as part of my PhD project to evolve the fluid quantities, including the magnetic field, on a moving mesh that traces the fluid motions. And this is a great method for being able to automatically adapt to where galaxies form inside your box. We have this huge dynamic range problem where you have very small galaxies and very large voids. So the moving mesh is great at adapting and with minimal advection errors because the mesh moves. And so I'd like to take a step. So that's a summary of the numerical methods behind the simulations. So I'd like to take a step back and just show a different set of simulations from some earlier work, which is dark matter only, where I show some idealized, virialized fuzzy dark matter halos. And these simulations started off with toy initial conditions. So I'm just merging a few random overdensities through gravity, and this is showing the dark matter density visualized as these density isocontours. And everything collapses through self-gravity until you form a single halo. And inside, you can see the soliton core. And on the outside, you can see some fluctuations in the dark matter. And this is due to the interference patterns that you have generally an approximately uniform velocity dispersion in the halo of the dark matter. And so you have all these wave vectors pointing in different directions, and you obtain naturally some interference from the superposition of those. And so if you run a bunch of these simulations, you always find a core at the center with maybe a roughly r to the minus 3 outer profile, in some cases slightly flatter. So r to the minus 2 would be an isothermal profile. And then you see this, you do see this nice core. This core is soliton and has a very particular analytic solution. You can see that if everything is normalized by the central density and a core radius, which is where the density falls off by a factor of 1 over e, then everything's self-similar. And all these lines on top collapse to a single line on the bottom. And I just like to remind everyone that, in contrast, the cold dark matter NFW profiles give you a cuspy r to the minus 1 inner profile and an r to the minus 3 outer profile, which is some. So the other profile is similar. Okay, so here I'm just showing the evolution of the energy densities in this dark matter superfluid. There's 3 components here. There's the potential energy. Okay, call this W, and there's the kinetic energy, which can be decomposed into the classical component and and an additional component due to density gradients, which is an additional quantum-like contribution. So kV is your 1/2 mv squared that you might be familiar with classical energies, and then with this additional quantum component. And these energies in the halo are in approximate virial equilibrium, which is just Ehrenfest's theorem in quantum mechanics. And we can go into the simulation and study the scaling between the core mass and the halo mass. And these simulations show a fundamental scaling relation where the core mass to halo mass scales as this dimensionless quantity involving the total energy of the halo. And this type of scaling, I point out in my work, has a physical meaning where the binding energy of the core and the halo are proportional to each other. And in cosmological simulations from other groups, like Shive's simulations, show a slightly different scaling relation, and so they have a power here to the 1/2, and the meaning of this could be that the halos in a cosmological setting are not fully virialized. There's also other interesting properties of these simulations we can study. So there is something called quantum turbulence, which is that the superfluid, the Schrodinger equations are irrotational, and you can only have vorticity organized into locations where the density is 0, and you have this singularity in your phase and a Winding number about it. And so the vorticities arranged into this tangle of vortex lines. So we can go, and this is known from superfluid, theory and study of systems in condensed dark matter, in condensed matter systems in other areas of physics. And then we can go into the dark matter simulations and look at whether we see something similar, study the power spectrum, and whether we can detect these vortex lines, and is this type of is the power spectrum similar to Kolmogorov theory for classical turbulence, or is it something else, like k to the -1? And it turns out it in our simulations we do see this k to the -1 signature, which tends to be called thermal turbulence in condensed matter theory. And so what's being visualized here is a slice showing how the vortex lines are visible in slice, and on left is some power spectra, and I'm showing numerical convergence with increased resolution to this -1 like slope. And so just to summarize, the halos are defined, so fully virialized fuzzy dark matter halos are defined by a soliton core, and in the absolute theoretical limit, you'd expect an r to the -2 outer profile when everything's isothermal. And the numerical simulations have shown that you can show this, you can reach this quasi-steady state in fuzzy dark matter theory, which is quite interesting because in cold dark matter theory, there isn't really a quasi-steady virial limit because there's nothing regularizing your equations, and you have the singularity at the center. And then you have this relationship between the core and the halo, and the idealized limit has this proportionality between the binding energies of the core and the halo. And the cosmological simulations show instead something else. So the physical interpretation there is that the core size is roughly equal to the velocity dispersion, to the de Broglie wavelength of the velocity dispersion in the outer part of the halo. So the cosmological simulations predict slightly less massive cores that are also larger. Okay, so as we continue, I'd just like to highlight just a few other, like zooming in now to the small scale structures of fuzzy dark matter. Some student works touching upon dynamical heating, friction, and concentration about fuzzy dark, about supermassive black holes. So the first one is work with Jerry Ostriker and the student Ben Church. This paper is led by Ben, calculating the dynamical heating that you'd get in the Milky Way, in the Milky Way, due to those interference patterns that you saw from the movie. And these interference patterns would couple through gravity to the stars, in particular the old stellar disk in the Milky Way, and that would heat the stars and give it some thickness, some velocity dispersion. And observations put that at maybe around 30 kilometers per second. And so Ben calculated how the velocity dispersion would look like if the old stellar disk is only heated due to dark matter substructure. And here we're comparing fuzzy dark matter and cold dark matter. So in cold dark matter, you do have heating from subhalos, and you have this line, this white dashed line. You can see that subhalos heat the outer part of the old stellar disk out to kiloparsec, radius of 15 kiloparsec or so. In the fuzzy dark matter models, you have less heating due to subhalos because there's less substructure. So it's this blue line, but you have this additional heating due to the interference patterns. And what's being shown here is how different particle masses, if you decrease the particle mass, then you increase the heating. And at some point, you go beyond this 30 kilometers per second limit at around 10 to the minus, a few times 10 to the minus 22. So this sets, so this calculation sets a lower limit on what the particle mass could be. So another interesting related concept is dynamical friction in fuzzy dark matter. And I'll just highlight the overall concept here, which is that you have satellite galaxies falling into a central halo, and these satellite galaxies have some relative velocity with respect to the dark matter background, and its motion ends up producing a wake, which gravitationally will slow down and produce a drag on the satellite, and ultimately lead to its in-spiral and infall into the central halo. So there is this satellite timing infall problem, which observationally we do see many satellite galaxies that we might have predicted would have already fallen into the center halo if you assume cold dark matter and calculate dynamical friction for cold dark matter. And so one thing we highlighted, so one thing these students Lachlan and Kara highlighted in their work is that in fuzzy dark matter, the dynamical friction is much reduced, which can actually alleviate some of these problems. And we were able to test some of the known analytic calculations with some more self-consistent simulations of dark matter and match the theory. But we also identified some interesting regimes where you can actually have deviations from the analytic theory, depending on whether there's velocity dispersion in your background fluid, or whether everything's just dominated by the quantum pressure. So there is this mixed regime for the dynamical friction, and I don't have time to go into this today, but I'm happy to talk about it after the talk. But on the whole, dynamical friction in most regimes tends to be reduced from cold dark matter, but in certain limits, it can be actually increased. One particular area would be the final parsec problem for the merging of two black holes, which would be an area of further study. But in that case, you'd be in this quantum pressure regime where cold dark matter would predict no dynamical friction, but fuzzy dark matter continues to predict a source of dynamical friction. So finally, a third project, speaking of black holes, is this project by Elliot Davies, where he considered how would the dark matter organize itself about a supermassive black hole, and whether this organized structure would be stable and long-lived within the lifetime of the universe, because as you know, there is the no-hair theorem. So zero angular momentum structure about the supermassive black hole will ultimately have to be absorbed by the black hole. But because there is the separation of scale, it can still be long-lived. And what Elliot showed is that in the limit where you have a soliton core with a massive supermassive black hole at the center, it would reshape the soliton to become more compact. You end up with something that's more like a hydrogen Bohr-like solution with an exponential profile, and these structures could be long-lived. So you would have this concentration of dark matter about the black hole. And then you can place constraints on the dark matter particle mass because from observations. So by looking at, for example, M87, or also observations of the Milky Way, both of these have various constraints on how much dark matter can be centrally concentrated about the black hole. So in M87, for example, observationally, you can infer how much matter is within 10 parsecs of the center from velocity dispersion in the stars, and also independently in measurements of gas. And recently, M87 has been imaged by the Event Horizon Telescope, and so you know the mass of just the black hole itself from the size of the Event Horizon. And so you know how much leftover mass there is within 10 parsecs, and if everything's due to dark matter, then you have to make sure that your analytic models with fuzzy dark matter don't predict a concentration of dark matter that would violate that. And so with this work, we were able, Elliot was able to roll out a narrow range of dark matter masses slightly below 10 to the minus 22 eV using M87. So we have about 8 minutes left. So I'd like to just conclude with this discussion of the connection between the Laplace-Poisson equations and the Schrödinger-Poisson equations, and what happens as you make the fuzzy dark matter particle mass large, and answer this question about we've seen that they do approximate to each other in some sense, and how is this possible when the Schrödinger equations are three-dimensional and the Laplace-Poisson equations are six-dimensional? And the answer in part has to do with the superposition property of the wave equations, but we can explore this limit in a formal sense. So I can start out with some toy initial conditions and look at the evolution of the density. And you can see on the left, I have a low axion mass. In the middle, I'm increasing the axion mass, and the right is a classical n-body solution. And there are differences in the density structure. The density does not converge. There's always these order unity fluctuations due to interference in the wavelike models, but there is this formal convergence shown on the bottom right in the gravitational potential field that scales as particle mass to the minus 2 power. And similarly, the acceleration field converges as m to the minus 1 power, which means that the behavior of any baryonic matter that's coupled to the dark matter only through gravity will also formally approach the classical limit. And so there is there is this nice convergence to the classical solution as you increase the axion mass. And we can test this idea in cosmological simulations too. Here, it's of course much hard. It's quite hard to go up to very large axion masses. So here I've selected two. The larger one is 10 to the minus 21 eV. And I'm just looking at this radial profile of this most massive halo. And at the lowest axion mass, everything is just a single dominated by a single soliton. Higher axion mass, you do have a compact soliton, which regularizes your central singularity. But you do have this break from r to the minus 1 to r to the minus 3. So this is NFW-like, and it agrees with the classical solution shown in purple. And you can see this also deviates from the idealized simulations. So to summarize, the classical limit for the potential field is recovered as order m to the minus 2 classical, and the force field is order m to the minus 1. Soliton cores regularize caustics and central singularities of halos. And so in cosmological contexts, fuzzy dark matter is NFW-like with soliton core. So just in the last minute before questions, I'd like to say that there's still a lot of future work to be done to understand all the astrophysical and cosmological consequences of fuzzy dark matter. And these include making these simulations bigger to larger boxes so we can study Lyman alpha forest more precisely and really get a handle on the nonlinear evolution of the halo mass function. Because as I've highlighted, there is this nonlinear formation channel which can produce low mass solitons that are 1 to 2 orders of magnitude below linear theory predictions. And there's also more to be done with small scale structures, so including dynamic soliton black hole interaction, thinking about stellar streams, and about more of these dynamical timing problems. And there is still this catch-22 problem that needs to be resolved. This moderate tension between setting the particle mass, to capture these large cores, but also the right level of substructure. And the resolution for that could be that we might be able to rule out that dark matter is not fuzzy. We're not there yet, but the tension is also not resolved. it could be that there is these nonlinear structure formation effects could alleviate this tension, as well as the wave interference patterns. At least they go in the right direction, which the numerical results show. You can also have, of course, baryons affecting results. But there's this final point that I'd like to make is, which is to go beyond the model and the simplest model for fuzzy dark matter and start adding in more self-consistent physics. So when is this weak attractive self-interaction term that would actually naturally be present in the equations which arises from the strong CP symmetry breaking scale? And the starting point, write down some action for your scalar field in the early universe, and F is your decay constant. And if you expand everything into the non-relativistic limit, this is the equation you should be working with, the Schrodinger-Poisson equation, but now you have this additional term in equation 10 on the right-hand side, which traces back to this introducing F, your decay constant. And you can see that this is a very weak effect, weak negative, there's this negative sign, so it's an attractive self-interacting term, a nonlinear term, and this is usually just dropped from the simulations because this effective scattering cross-section is very small. But recently it's been shown in analytic work that maybe it might not be such a good idea to drop this term because even though if it's small, it can still start affecting cosmological small-scale structures. So I'm just testing this idea here with very small values of A in some preliminary simulations, and I'm showing that there these preliminary results seem to show that you can actually introduce a completely new type of substructure in the fuzzy dark matter, which could potentially resolve some of these outstanding tensions. So I think I'll end here. Okay, I'll just advertise that Schrodinger-Poisson equations can be applied to very different systems as well, such as just arbitrary scalar fields in the early universe. And we've done some exciting work with Mustafa Amin at Rice University, thinking about the nonlinear evolution of such a field and production of gravitational wave background signatures. But just to summarize everything and just save some time for questions, I'd like to point out fuzzy dark matter is a physically motivated alternative candidate to cold dark matter, and there are many interesting modifications to small scale structure, very unique predictions, well-defined predictions that can be testable in the next 5 years. And in particular, first galaxies is one area where you could see large differences between fuzzy dark matter and cold dark matter. I love the rich mathematical structure as well, and this idea that quantum mechanics can approximate the classical limit if you make the particle mass large. And so future work needs to be still done with constraining this dark matter model and I think much of the future relies on increasing the power and the accuracy and the size of these fully self-consistent cosmological simulations. So that concludes my talk for today. I'm again very thankful that I had this chance to visit everyone virtually, and happy to take questions.
Philip, thank you very much for your talk and visiting us in Patras.
Thank you.
And there are some raised hands. Andreas has a question. So Andreas, if you want to turn on your mic and ask your question.
Hello.
Hi.
Thank you for your talk. Your simulations are amazing. I have some questions for you I would like to ask.
Please.
One of the main motivations for fuzzy dark matter is its explanation of the Caspi halo problem, Caspi core problem. And you talked about the James Webb Space Telescope. I would like to ask, will we have some results for observations for cores other than just structures for galaxies? Will we have some results to confirm the existence of fuzzy dark matter from the James Webb Space Telescope?
Oh yeah, yeah, great question. So you mentioned the cusp core problem, and so okay, so from the James Webb Space Telescope, what I'm envisioning is that if dark matter is fuzzy dark matter like or warm dark matter like and the mass is below some certain value, then you would off the bat be able to at first light be able to observe these very filamentary first galaxies, assuming that the baryonic formation, the star formation processes are also similar to what's captured by these cosmological simulations, and that would be just an immediate qualitative result. Yeah, you talked about the core cusp problem, and I think where most of the future work there will happen might be with some Gaia data of nearby satellites will start revealing to greater precision the precise nature of the you can infer the coordinator of more satellites to higher precision at multiple radii, because now you have five-dimensional information, and so in the next 5 years, I imagine we'll see a lot of new constraints because there's Sculptor and Fornax, which are some of the best systems out there, but we can do better by both extending that population and also getting better quality data.
Okay, I would also like to ask a few more things, if you don't mind.
Yes.
Doing computational simulations, I would like to ask you what are some of the challenges to create a simulation with both dark matter and baryonic matter?
Yes. Yeah. Great questions. So one of the biggest computational challenges when it comes to fuzzy dark matter is actually just in the dark matter component, which is that the simulations are expensive and you can no longer use particle-like methods. Well, there are actually some recent development in using particle-like methods, which I think show a lot of promise. But when you're using these spectral methods, you can guarantee an exponentially converged solution, but it's also very memory expensive. And then there is this additional challenge of how to couple the baryonic matter and the dark matter, and so and everything's just coupled to gravity. So you cannot so you cannot evolve the time system independently. So this is why, in particular, I use the second order kick drift kick scheme for evolving fuzzy dark matter, which is the same time stepping scheme that baryons are evolved on in most modern cosmological scales. And then the challenge there in connecting the two components is just calculating the total self potential from the dark matter and the baryons. So if you just have the dark matter, then this is a much simpler problem because everything's on a grid, and you can solve Poisson's equation like I've shown using the Fourier method. And once you get into baryons, there is an additional complication where to get things right, you have to go beyond that. You have to use fast multipole methods to do the calculation efficiently. And
okay.
Yeah, and there's many other areas of the numerical method I could talk about if you'd like.
Right. Are there any other questions?
I I have some more questions.
Okay, I know, Andreas, that you have some, but in case someone else wants to ask a question, and then if not, we can come back to you. Okay, I see no raised hands. So, Andreas, you can ask your question, and I have another one that I want to ask, which is probably relevant, but please go ahead.
Okay. So I would like to ask, so far, have we had any experimental data that motivates the fuzzy dark matter model? Anything that makes it look like it's a possible scenario? I don't know.
Oh, you mean based on lab experiments or direct
Yeah, anything.
axion searches? Yes. So as far as I know, no, there are searches being built, but current experiments such as the ones at University of Washington with ADMX, and but those searches are, so I would say that most laboratory searches are not focused on the 10 to the minus 22 EV. They are more focused on this QCD axion mass range because those are easier. And so as far as I know, yeah, there are no lab-based experimental observations or constraints on this ultralight scale.
Okay. So another question I would like to ask is about the fast dark matter model. You talked about catch-20. Oh, wait. Does Mr. Gourgouliatos want to ask, or should I?
Yes,
go?
I will ask a question, and Andreas, you can come back. So, Philip, in the model you have shown, well, that the cold dark matter gives us the usual picture of the cosmic web. The warm dark matter gives us the caustics, and the fuzzy dark matter gives us these interference patterns. These look strikingly different to me, at least, and I'm wondering if this would be observable. I mean, essentially, the other two pictures seem to be, very, very different. Now, I don't know if it's the fact that I have been used to seeing the cold dark matter simulations and they look so different to me, or if it's something that we can rule out with current observations.
Yeah, that's a great question, and so of course, when you're looking at projected densities, there is a striking difference between fuzzy dark matter and warm dark matter when you have the interference patterns in one of them, and the observational limitation is, of course, you cannot observe this directly. If you think about the so the most of the effects can only be captured by the gravitational coupling to ordinary dark matter, and these interference patterns are high K, small physical length scale structures, so its impact on the baryonic matters is not as big. You can see that the baryonic matter itself does not organize into these interference-like structures, but perhaps one area might be where I haven't done much work on, but there remains a lot to do, would be gravitational lensing, where that can give you more direct probes of projected densities. And there is so there, fuzzy dark matter would make this unique prediction because you have this uniform structure in halos with a very specific prescribed power spectrum. So perhaps that's the best way to detect the interference patterns. I mean, there are other indirect effects that you can think about, like the heating of the stellar component in the in galaxies, but that's like I said, indirect.
Right. Thank you very much, Philip. Now, I would like at this point to thank Philip for the seminar. Obviously, I will applaud on behalf of all the audience. Thank you very much.